Welcome to the Bazaar of Numbers. Meet Rohan, a hungry 7th grader who just arrived at his favorite spot, the Samosa Cafe. A single samosa is 20 rupees. This stubborn price never changes. In math, a permanent value like this is a constant. 1 samosa is 20 times 1. 2 is 20 times 2. The amount changes, but the constant 20 stays frozen. Constants provide a reliable foundation for basic math because their values are guaranteed. But math often leaves the market. Imagine a cricket match where the batsman launches a ball high into the night sky. While the ball is in the air, we know the team has scored, but the exact number is a mystery. It could be 4 runs, or it could be 6. Arithmetic stalls in this moment. You cannot calculate a final score when a crucial piece of numerical data is missing. Real-world problems frequently involve these temporary mysteries, requiring a tool that can navigate uncertainty. Algebra solves this by using letters, like x, as a shortcut for unknown values. This letter is called a variable, from the word vary. It is a temporary container for a mystery number. If the cricket ball lands inside the boundary rope, the container opens and x becomes 4. If it clears the stands, x shifts to 6. If the batsmen run between the wickets, it might become 2. A variable acts as a magical shape-shifting container, holding the value until the final result is known. When constants and variables work together, they can map out complex situations, like the cost of an afternoon at the arcade. The arcade charges a 50 rupee entry fee. This is the unchangeable constant. You pay it regardless of what you do inside. Once inside, you choose how many games to play. Since we don't know that number yet, we'll call it G. If each game costs 10 rupees, the total spent on gameplay is 10 multiplied by G, or simply 10G. To find the total budget, we combine the 50 rupee constant with the variable game cost, creating the expression 50 plus 10G. This combination is an algebraic expression. It uses numbers and letters as a team to decode a real-world puzzle. Back in the bazaar, Rohan watches the symbols on the screen, following how they interact. Algebra uses these letters to build universal formulas that work for any number you provide. While constants keep a formula grounded in known facts, variables provide the flexibility to handle the unknown. Try applying this logic yourself. Imagine Rohan plays exactly 3 games. In our formula, G is now replaced by 3. Multiply 10 by 3, add the 50 rupee constant, and write the final total for Rohan's arcade trip in the comments. Mastering the balance between the known and the unknown is how you move from basic counting to mastering numbers. See you in the next episode.
We're back in the arena. Last time, we built a formula to track Rohan's budget at the arcade, 50 plus 10 times G. This expression is built from distinct structural units called terms. Instead of a single mass of math, the expression functions like a train made of separate cars. You can find where one term ends and the next begins by looking at the plus and minus signs. In this expression, the 2 parts are divided by the plus sign. On the left is 50, our first term. On the right is 10G, our second term. This applies to any length of math. In the expression 4x squared minus 3x plus 7, the plus and minus signs act as barriers. By looking for those signs, we can see each unit, 4x squared, negative 3x, and 7. Organizing an expression into these individual units allows us to identify and manage each part of the formula separately. Let's look closer at the internal structure of a single term. In the term 10G, we need to define the specific role of the number 10. When a number is multiplied by a variable, it is called the coefficient. It acts as the multiplier, telling you how many times that variable repeats. If you have 10G, your coefficient is 10. If a term has a negative sign in front of it, like negative 5x, the coefficient includes the sign. Here, the multiplier for the variable x is negative 5. What happens when a variable like y stands alone? There is no visible number, but that doesn't mean the multiplier is 0. If it were 0, the term would vanish. When you see a variable by itself, it has an invisible coefficient, the number 1. 1 times y is still y. Every term has a coefficient that dictates its scale, whether positive, negative, or invisible. Understanding the structure of a term allows us to see how different terms interact. In algebra, terms are grouped into families. Terms that have the exact same variable are called like terms. Because these terms share the same variable, x, we can combine them. Adding 2x and 5x results in 7x. But look at 3x plus 4y. Different variables make them unlike terms. What happens if we try to add them? You cannot combine apples and bananas into a new fruit. Similarly, unlike terms refuse to simplify. They stay exactly as they are. Maintaining the distinction between unlike terms is essential for accurately simplifying any algebraic expression. Now that we've covered the rules of terms and coefficients, let's apply them to a single problem. This is your challenge expression: 7x plus 5y plus 3x. Analyze the expression to find the matching variables, combine the coefficients for the like terms, and simplify the expression to its shortest possible form. Remember, terms are blocks separated by plus and minus signs. The coefficient is the multiplier, and while like terms combine, unlike terms stay separate. Work out the math and leave your simplified expression in the comments below to confirm you've mastered these structural rules. See you next time!